Hello. So I'd like to present a couple of examples of how we solve these equations so you can see them worked. The first one will be a practical example on something called Newton's law of cooling to show you where it comes from and how to apply the techniques that we've already looked at. If we go over here and look at the background of this situation, we have by investigation find first that a hot liquid loses temperature quicker than a cooler one. So if the room, the environment is a certain temperature, the closer you are to the environment's temperature, the slower the temperature change occurs. Now this happens commonly, of course, with a coffee on the table, but understand something, this is part of how our heating systems work. One of the reasons that air conditioning is expensive is because we want a very compact device that does our air conditioning for us. Because if the temperature difference, and in the case of air conditioning, it generally can't be below freezing or it'll ice up, especially on a humid day in the summertime. So you might have base 20°C, maybe 25°C if you're lucky, difference in temperature between the condenser coils and the ambient outdoor air. And so that difference isn't very big. And so we need to have a large enough coil, but you still want to cycle that through like a window type air conditioner, so you're going to have fairly big coils to do this. However, I should point out, so because the temperature difference isn't particularly large, you need more time. Okay, and so in the case of an air conditioner, you can have a bigger coil, which in effect increases the time. Compare an air conditioner in the window with a small ceramic heater, because the heater coils can get as hot as the material can handle, literally hundreds of degrees above ambient. And so as the air comes through, there's a very rapid change. So small heaters are still very effective. But air conditioners are in a different set of circumstances. Now, if you have a larger device, and let's suppose you're circulating coolant through that isn't compressed, that isn't dealing with those factors, that may be 10°C instead of 2°C or something like that. The temperature rate of change, of course, will be yet again slower. But if you have a larger box of some device, then as the air goes through, you will still get the cooling effect. It just takes more time. If such a device is built into a home in a way that's unobtrusive, you could achieve these types of effects. So this principle here, whether it's a cup of coffee, it also is based on a lot of other physics that we use day to day. I should point out, for example, in the car, a compact air conditioner is, of course, pretty much essential because of the limited size of the engine compartment. And so there's some cases where we're going to have to go that direction. Anyhow, let's look at this for a moment. We have hot liquid cooling faster than a cooler one. This can easily do that with a thermometer. And with further investigation, we find that the rate of cooling is directly proportional to temperature. And so in other words, how fast it cools is a function of the difference in temperature, but in a linear way. Okay, it's not a square of the temperature or something like that. So let's look at our question here. So we're going to start at the temperature for the liquid. We'll call it initially T naught. So we're just going to do some basic background things just so you understand how we set up this equation. At infinity, an infinite amount of time, if you will, then the liquid, the coffee, will be the same temperature as the environment. Okay, so we'll take that to be a given. And so let's look and see what this means. The temperature at any given time, the difference between that temperature of the coffee and the environment is what we're talking about. The bigger this number, the faster it will cool. This is our prime. I could use a dot, but I did it as a prime in this case. And we have some arbitrary constant, generally based on the specific heat or whatever. We also have these basic conditions that at T0, whatever we come up with as a solution must equal the initial temperature of the coffee. And at an infinite time, it would have to equal the environment. And this is specific to any case like this. Once again, now we take our temperature, we have the initial temperature T of 0 equals T naught is equal to 52. T of 1 minute is equal to 42C, and the environmental temperature is equal to 24C. We know that the temperature change, T dot, is equal to some constant, and of course the temperature of the material is getting cooler. So we're losing, it's a negative value, and we can leave it as a positive, but we have to be careful here because we have to make sure that K is computed as a negative. We have to know that. So let's make it a negative here because we know it's negative. And then it's going to be the temperature of the material, so T, minus the environmental temperature. So when it first came off the coffee maker, you have a big difference here times this K. That implies that it's cooling faster. If this is pretty close to the environment, then although it's cooling, it's much slower. Okay? So we'll just base it on that logic. So then we have T dot. Now we're going to have plus KT is equal to, so this is coming across and this is canceling. We got K sub TE. So there's our basic first order differential equation. Now we're going to solve this using an integrating factor. So if we take I is equal to e to the integral of P of x dx as our general example. So for this one then, integral of P of x dx is going to be equal to the integral, well, what do we have here? Here's our equation, and here's our variable, which in this case is k. So we have the integral of k dt, which is the variable of interest here, and this is simply going to be kt. So the integrating factor then is equal to e times kt. Now we will put this in the equation. So we have by multiplying e to the kt, and then plus k t e to the kt is equal to, and then k once again, e to the kt times the environmental temperature. And so once, as we already have learned with our first order arguments and instruction, this is simply such as it is going to be t e to the kt quantity. The product rule here, okay, if we, it's f prime g times g prime f, so this is the prime here, that's the function, and then the derivative of this is simply k e to the kt times the original function. And of course over here we just have the same variable, nothing different. And notice here that now we have a function of time, we also have these two constants. In fact, I think I'll recast this briefly. So we have k t sub e to the kt. Just so we understand, these are constants, not dynamic variables. Integrating. We have t e to the kt is equal to k t sub e times the integral, so I'll make a parenthesis here, of e to the kt dt, and that's k t sub e. So the integral of this is going to be e to the kt over k plus a constant. So now we'll clean up the right side. Once again, we have t e to the kt on the left. We'll leave that still as it is. On the right side, we have to multiply both terms. K times this is going to cancel. Okay? So we're going to have simply t sub e to the kt. And then we'll have this times this constant. It's just a constant. I know it's frustrating, kt sub e times c is just a constant, but that's what it is. A constant times a constant is a constant. And until we actually substitute these numbers in, it doesn't really make any difference. And so as a consequence, we will have t sub e, e to the kt, plus a constant. And so we should be okay there, I think. Now we'll divide. And we get t is equal to, so when we divide through by e to the kt, we're going to get t sub e plus c e to the minus kt. Okay? Because this is now in the denominator, so we can make the exponent negative, and we get this arrangement. Now that's as far as we can go without putting in some variables. And we have no negatives, so we're okay so far. So t of 0 is equal to 52, I believe. There we go. And so that means then that 52 is equal to 24, which is the temperature of the environment. Okay. Plus c. Now, e to the minus kt, well, t is 0. That's going to make this whole thing 1. So that makes c 28. Now, the other half, of course, is a t of 1 equals 42. And so that means then that 42 is equal to, and we're basing everything on this equation yet again, so 24 plus 28 times e to the minus k. Because this t here is 1. So it'll simply be e to the negative k. Well, okay, well, let's see what this looks like. So we subtract the 24 from 42. We'll get 18, I guess. So 18, still positive, right? But remember, this is negative k. Divided by 28 equals e to the negative k. So we take the logarithm, ln of 18 over 28 is equal to negative k. And then k is equal to, so I'll pull up my old calculator here, and we get 18 divided by 28, and we take the ln of the answer, we get yes, so the k then is going to be 0.442, say. So our differential equation now, in terms of time, t of t then, is going to equal, so we'll go back to our initial answer, which is this one, is 24 plus 28 e to the minus 0.442 times time. So when this is 0, this difference is a maximum. You'll just simply add these two numbers. When this is negative infinity, or positive infinity, pardon me, this term will be 0, and this will be the environment. So that checks. So now we're going to check and see, so just testing. T at 0 is equal to 24 plus 28 equals 52. That looks good. And t at infinity is equal to 24 plus 0 equals 24, which is what it's supposed to be. So just as a back, sort of the law of extremes kind of thing here. All right, now let's evaluate t of 10, pardon me, which is what you're asked to do with the question. You have 24 plus 28 e to the minus 0.442 times 10. So let's see what we get. So second e to the x, we're going to have negative 4.42, is equal to, and then we're going to multiply that by 28, and we get 336. So the coffee has gotten cold pretty fast. So this is equal to 24 plus 0.337, say, and then is equal to 24.337 degrees. Now, if, for example, the decline after 1 minute had not been so precipitous, had been perhaps, say, this was say only 50 degrees, that would change the value of K. All right? So just for sport, we'll do that just to show you how this can change. So we'll use another color here just to illustrate this. So let's suppose we have, leave everything else the same, and we'll just have, after 1 minute, it's just down to 50. So we're okay until we get to this one. So we would have 50 here. And then you'd be subtracting 24, which would now be 26 instead of 18. So it'd be 26. So you're getting a lot closer to 1. And so now you have, in this example, K now equals negative 0.074 perhaps. And if that was the case, so now we have, everything else is the same, but we're going to have e to the negative 0.074, okay? Now we can look and see what would happen there. So now we have e to the x, and in this case multiplying by 10 would be e to the negative 0.74, which is 477 times 28, would be 13.35. So in this case it would be 24 plus 13.4, just for simple math, and this would give us something in the neighborhood of 37 degrees C. So in the one case, if we were to draw, just do it as an example here, if we were to draw the curve, the exponential curve, in the initial case I gave, the decline is precipitous, okay? In the orange case, it's more gentle, even though it's an exponential function. So the point here, as I tried to explain before about air conditioning, and so to enhance the point I was making earlier about the air conditioner and how it's affected by this law of cooling. So air conditioners, generally speaking, will want to have their coils above 0 degrees Celsius for the most part. Otherwise, the coil will freeze. Oftentimes in the summertime, the air is quite humid, so there'd be a fair amount of moisture collecting on the coil and causing icing, which can block passage of the air or require expensive, complicated heating systems that periodically melt the coil ice. So if we start off with just the basic version where we're going to keep that temperature just a little bit above 0. On the other hand, we want the temperature coming out of the air conditioner, or at least of the coil, to be as close to 0 as we can get it within the engineering. But the room might be, if it's, let's say it's kind of warm, even if it goes high as 30, so the difference in temperature is not very high. It's maybe 25 degrees or something like that. If you look at a furnace, as I mentioned earlier on, the temperature of the heating element could be 500 or 600 C, maybe even more. And so the difference you achieve with a heater is not constrained by boiling or anything else for the most part, other than just the property of the materials. So you get a large difference in temperature, and thus the heat transfer occurs very quickly, and therefore you can make the heating units smaller. Air conditioners don't have a much greater constraint. And so if we come over here, just to show you an example, we can look at this a couple of ways. First, if you imagine the heater, you want to achieve a certain difference in temperature of the air coming out of the unit. Okay? If it's very steep like this, that means there's a large difference in temperature that's being created by this device. Okay, and therefore the exposure to that difference need only be for a comparatively brief time. This allows the unit to be smaller in construction and still produce the appropriate effect. If you have a different kind of system, which is in one way less efficient, okay, the difference in temperature you desire is this, but it's going to take a lot longer for this to accomplish. Now, for the air to stay inside an air conditioner for 4 times as long and so forth would require complicated ducting and probably end up with other problems. So this would otherwise result in a larger unit so that the air would have more time to flow through the air conditioner. Okay, and this is generally not considered practical for window applications and even for central air conditioning. So we generally work with the compressor system by bringing that temperature down as quick as we can to therefore reduce the time and make the units as small as we can. If, for example, you took a hose and buried it in your backyard and ran water through it or antifreeze or whatever, when you're down about 1.5 meters, the temperature basically stays the same all year round. It's around 10, maybe 5°C, something like, depending where you live. And so that's, reasonably, would be perceived to be cool as well. But it's not as cool as the air conditioner, so it would take longer for that, because by the time it might even be 10°C, and the difference you get is less. And we can see that those differences really matter in the sense of the cooling effect. So if you had an air conditioner that didn't use compressors and circulated water, you would have to have a lot bigger unit to allow the air to flow through it to get the temperature difference you're looking for. Now, in environmentally conscious homes, this is one of the things that you could consider doing. The other thing that we should be looking at in this example is that it's much better to pull air, in other words, create a low pressure and suck air through a system than to try to push it through with a fan. And most of the time right now, our systems are, well, they're doing both in a sense with a squirrel cage fan, but in my view, they're less efficient. If, on the other hand, you had registers with mini fans on them, you could draw air through your system and only turn on the ones you want. The other problem we face with furnaces is that because of the high temperature of the furnace, the air has to flow through the furnace, or you will end up causing a failure or a fire or melting something or whatever, because you could fire in there. So that's a concern. So once again, here you notice, for example, at home, if you turn off the heat, if you have a central system, you'll notice that the furnace runs for a little while, because when you turn it off, the burner goes out, but then the blower will continue to run until the whole thing is cooled off sufficiently that it can shut off. If you used, for example, water off of a solar panel through the same system, and the temperature of the water coming off the panel might be 40°C, let's just take a number, and you'd like your home to be 20. Once again, the difference in temperature is fairly small compared to, let's say, it would be with fire or whatever, or electric heat, where you can have very substantial differences in temperature. So once again, we need this long time frame to create the difference. But once again, we don't need the fire, we don't need in the same expense, and we can circulate water at reasonable paces. So it is an interesting system to look at, but it's all based on this Newton's law of cooling, and thus how quickly the heat is exchanged between materials. Now there are factors, of course, but this is a course first look at the logic behind it, okay? And so this can give you an example of why heaters are smaller, why air conditioners in comparison for the same effect are larger, and why why we have to use compressors in air conditioners, because we really want to create that big delta T. And if we use other types of means, that delta T is much, much smaller, and it makes it comparatively hard to get the desired cooling effect. And so, worked example with some explanation and practical example. Hopefully it was interesting for you. And the next step here now, we will look at a second order equation. So as promised, when I introduced non-homogeneous second order differential equations, I said that I would give you yet another example of an oscillatory case and also one where the first guess doesn't work out. So here we go. We use the same equation we had earlier. Let's save some time. And so as we just put here, recall the homogeneous case our solution, shall we say, is y equals c1 e to the 6t plus c2 e to the minus 2t. The other example I gave you, that's shown, but it's particularly difficult. So now we want to determine what the third term of this solution will be that will satisfy this term. So once again, the third term of this differential equation has to satisfy this term because these two generate a zero here. So therefore, only the last term is going to create something that would then agree with this. So that's why we can do it this way. And so we will try for a solution using y sub h equals a sine 2t. We're going to use the function that's here. And of course, because it's the method of undetermined coefficients, we put in an unknown. All right, let's do, and it's often good in these cases to do your derivatives ahead of time so that if something goes wrong, you can go back and try and find out where the mistake was made. So y sub h prime is going to be 2a cos 2t, and y double prime h will be negative 4a sine 2t. And so now we substitute these into the differential equation and see if we put these three terms on this side, do we get this or do we get something else? And that's how we'll know if our guess was a good one or not. Okay, so we have minus 4a sine 2t minus 4 times quantity 2a cos 2t, and then minus 12 quantity a sine 2t. Okay, so let's evaluate this. And we're going to have to see if we have, because we have coses and sines here, let's just see what we get. So we would have for the sine 2t, we're going to have minus 4a and minus 12a. So we'll have negative minus 4a minus 12a times there. And then for the cosine function, cos 2t, we'll have negative 8a. To zero the cos term, the cos 2t term, a equals 0. But this would also imply that negative 16a sine 2t would also equal 0, and this of course is not equal to the desired sine of 2t term that we have. So this is a failure of our first guess. This does not work. One of the advantages though is often if you have a sine function, because they're so related, you may well also have a cosine function. So your plan B here is pretty straightforward, and you could try, so our second guess then might be so then we have y sub h is equal to a sine 2t plus b cos. And again, reminding that a and b are real, and they're generally constants. So, once again, we just approach it exactly the way we did a minute ago. So y prime. So these initial derivatives will be the same ones we just did. 2a cos 2t minus 2b sine 2t. Y double prime is going to be negative 4a sine 2t. And this one, we're going to take here, we're going to negative 4b cos. So some of these complicated equations, really the thing we have to do is to be careful and take our time, because it's the slightest mistake and it's all over. And the more involved these things get, so that's why I like to write things out in a bit more detail. And if I have to go back over it, I can look at each line. There is not a great amount of deductive logic, so I can generally see if I actually did it correctly or made some silly mistake. Substituting this into the equation, so then we get, well, once again, we just have to follow the path here. We just have to be careful with these coefficients that we don't switch signs in some way and make a mess. So the first one is easy. There's no coefficients. We have 4a sine 2t minus 4b cos. And then we have minus 4 times 20. I'll put it on a separate line here to make it a bit easier to see. Here's our derivative. And we have 2a cos 2t minus 2b sine. And finally, we have the function minus 12 times our original guess. Well, it's our second guess, if you will, but the function itself. Now, one of the things, the reasons why I like to do it this way is that when you multiply this out, we have a negative 4 here, we have a negative here, and otherwise there's positives. We have to take our time and be very careful that we do this correctly. It isn't intrinsically difficult, but we can make it so by haste. And I am as guilty of that as anyone. This is my third go through this. One of the advantages of making videos is that you don't get to see the crap. At least not unless when it's live, then we'll get a chance to see all of my imperfections may want large. Okay, so now what we're going to do here is we'll sum up our terms. So we're going to see our sine 2t coefficients and our cosine 2t coefficients. And we won't be too fancy here. Let's take our time on this. So I've got a minus 4a here. I've got a negative 8a here. See, that's a cos. So there you go. So that's what can happen. So minus 4a. Let's just do it like that. Get a little bit of exercise here. Got minus 4a. I'm looking for sine here. Sine. So that was the first term. The second term, my sine is over here. And I'm going to have minus 4 times 2b. So that's plus 8b. Okay, and then the main term here, I've got minus 12a sine 2t, so we'll put that in as well. Similarly, for the cosine, we have minus 4b. And then we have, for this we have negative 8a. finally, we have negative 12b. I just want to remind myself here. So this was sine to cos is okay. And cos to sine, yes. And then here we have cos to sine and another 2. Here we have sine to cos, another 2 that stays negative. Right. Okay, hopefully we're in good shape here. So we need, this is going to be negative 8a minus 12b, and this is for the cosine term. We want it to be 0. And for the sine term, we have negative 16a plus 8b equals 1. So if we multiply this out now, we're going to have minus 16 times minus 2 is plus 32, plus 8 gives us 40b. Equals 1. B then is equal to 1/40. Okay? And A, being negative 2b, A will then equal negative 1/20. And we should have our solution. I'll just check and see. Yep. And so, finally, our non-homogeneous coefficient then is going to be negative 120 sine 2t plus 1/40 cos 2t. Just for completeness, the final answer of the equation is in total, without the initial conditions, and so there you have the solution. So I thought this was instructive. We do get oscillatory functions, and you have a case here where the first guess was wrong, but it does show you how it's done. And again, for these type of equations, we're not going to be choosing last terms that are as obtuse that will keep us too busy, because the issue here is to look at what we're trying to accomplish, not trying to find a way to make it so technically difficult. So there you go. Thank you for watching these 2 examples of how to solve differential equations in practice. And hopefully you'll find this information useful, and if you do, I'm looking forward to helping as many people as I can. Please consider telling a friend, subscribe to my channel, and thank you so much for watching.